In this example, I'll show you how to apply Gauss's law to three simple cases. Case A, we're going to consider just a point charge plus Q. Now we have to choose a Gaussian surface through which the electric field is everywhere parallel to the area vector, and we only have two choices of Gaussian surfaces for this course. They're either going to be spheres or they're going to be cylinders. Anytime you have a spherical charge symmetry, we're going to use a spherical Gaussian surface. So let's say we want the electric field here. That is where you put your Gaussian surface, through the point where you want the electric field. So I'll draw my Gaussian surface as a sphere through that point, and the distance from the center of the charge to the point where I want the field I'll call R. Now we just have to apply the working form of Gauss's law. It says that E is equal to the charge inside that Gaussian surface over the surface area of the Gaussian surface over epsilon naught. And we can see in this case the charge inside that sphere is just exactly equal to Q. The surface area of a sphere, which you'll have to remember, is 4 pi r squared. And the electric field is everywhere parallel to any area vector on that Gaussian surface. So we consider the entire area of the Gaussian surface 4 pi r squared epsilon naught. And sure enough, we just get the equation of the electric field due to a point charge. Now for case B, we'll consider an infinitely long line of charge. It'll be positively charged, and I'll define its linear charge density as lambda, which is charge per length. So let's say we want the electric field here. That is where I'm going to put my Gaussian surface's edge. And for any kind of cylindrical symmetry like this, we're going to use a cylindrical Gaussian surface. So the Gaussian surface is finite, even though the line of charge is infinite. So I'll put my cylindrical Gaussian surface like that. Distance from the line of charge will be r, and the length of the Gaussian surface will be some finite length L. Now the amount of charge inside that Gaussian surface is just what gets cut out by that cylinder. So Q in this case, is just the linear charge density times the length inside that cylinder. Now the area that we're going to use for this calculation of the electric field is only the area through which the electric field is parallel to the area vector. And so that's only the curvy side of this Gaussian surface, not the top and the bottom. So our area is 2 pi r L. So putting that together into Gauss's law, we have the electric field at that point is equal to Q in, which is lambda L, over A, 2 pi r L, epsilon naught. And notice how the L's cancel. The L's will always have to cancel because the size of your Gaussian surface is completely arbitrary. So this becomes lambda over 2 pi epsilon naught r, or 2k lambda over r. Okay. The third case I'll show you is for an infinite sheet of charge. So we'll draw a sheet of charge. We'll have it positively charged. It's an insulating sheet of charge. And let's say we want the electric field here. Now this doesn't have spherical symmetry, nor does it really have cylindrical symmetry. However, the electric field everywhere around this sheet is perpendicular to the sheet. And so if I choose a cylindrical Gaussian surface going through this point, it will serve the purpose just fine. The bottom area of the Gaussian surface will be A. It doesn't really matter what the radius of the Gaussian surface is because the field doesn't pierce through the edge of the sides. So the amount of charge cookie cut it out by that cylinder will just be the amount of charge in that circle, and we'll define our area charge density Q over A for that sheet of charge, so that Q in is sigma times A, the cross-sectional area of that cylinder. Now the surfaces through which the electric field pierces parallel to the area vector are just the top and bottom areas of the cylinder, and there are two of them. So our A is actually going to be 2 times A, which is the area of the bottom and top of that Gaussian cylinder. So if we put that together into Gauss's law, we get that Q in is sigma A. The two surface areas through which the electric field pierces is 2A. Once again, the dimensions of the Gaussian surface have to cancel out because it's arbitrary. So we have sigma over 2 epsilon naught. And notice how the electric field does not depend upon how far away you are from the electric field. It's uniform out to infinity from that field.